Your Excellencies, welcome back here in the Weltsaal at the Federal Foreign Office for the Petersberg Climate Dialogue. And we have now an input coming up on the state of climate science. And for that, I directly hand over to the director of the Potsdam Institute for Climate Impact Research. With us today is Johann Rockström. Johann, the stage is yours.
Thank you so much, and welcome back after lunch. What I want to do is provide you with a science update, and just to connect back to where we were this morning. Scientifically, the task over the coming 7 months and 2 weeks is absolutely clear. We need to remove 3 billion tons of carbon dioxide from the global economy to have any chance of holding the 1.5 degrees Celsius pathway according to what science says is necessary. The representation in the room also emphasizing collective action is scientifically so strongly supported because we share the same small blue planet and the same collective action on one atmosphere that we cannot negotiate with. I want to give you the story of why we need to remove 3 billion tons of carbon dioxide from the global economy over this calendar year. I want to share with you the fact that we are today scientifically facing 2 reasons for deep concern that go beyond even the climate crisis that we've declared over the past 5 years. Number one is the signs we're now seeing of accelerated rate of warming. And the second is the question, are we seeing an Earth system that is losing its ability to buffer and dampen the stress that we're causing from human-induced climate change? Is the planet losing resilience? The evidence of accelerated warming comes out of course, the 5 different independent sources of temperature observations, where we have, as you have already highlighted today, breached through 1.5 degrees Celsius for the first time during 1 calendar year. That does not mean that we've breached the Paris 10-year moving average, but here is the concern. Since the 1970s until 2014, we have the big concern, which is the linear increase at roughly 0.2 degrees Celsius per decade of warming with aggregation of greenhouse gases in the atmosphere. And then suddenly over the last decade, the rate jumps up to almost 0.3 degrees Celsius per decade. What is happening? We don't really have the answer, but this creates a serious concern of a change in the climate sensitivity of the planet, which of course would reduce drastically the remaining carbon budget and change completely the necessities of the speed of reduction in emissions. And it's the same in the ocean. Just look at these numbers. The gray lines here is from 26 to 2022. Again, very concerning global increasing heat in the ocean. 90% of the heat from fossil fuel burning is in the ocean. And then suddenly you see the black arrow here, the jump, a 0.3 degrees Celsius jump suddenly in only 2 years, 2023 and 2024. Admittedly, this is an El Niño year. We also know it's a very active solar cycle, but it cannot explain the entire jump. And what is more concerning, look at 2025. Coming into March, where we are right now, we're still oscillating at this remarkably higher level of temperatures in the ocean, which should not have happened because we are now in a La Niña phase, which normally leads to a cooling of the global average temperature. What is happening? That's the big question. Are we seeing the first signs of a planet losing its capacity to buffer the pressures that we're causing on the planet? And that is something that we today are seeing massive amounts of investigation into, both in terms of are we seeing changing in human forcing, meaning our pressures to the system, or are we even, which I would argue is even worse, are we seeing a change in the feedback dynamics in the planet, the capacity of the planet to buffer the changes we're causing? There's a big debate around this. The World Meteorological Organization published just last week the state of the climate system for 2024, pinpointing the fact that, yes, there are natural variabilities here. El Niño, solar cycle, even a volcanic eruption in 2022, the Hunga Tonga volcanic eruption. But that is only explaining 1/3 to a half. We also need to factor in this, which is technical, admittedly, but I think everyone who really deals with climate action needs to now focus in on the fact that what is climate change? It is a human-caused energy imbalance. We're injecting heat into the system, watts per square meter. That's what you see here. Look at that fat line, which is the remarkable increase in heat into the system. Up until the black line you see vertically here, which is in 2010, carbon dioxide and total forcing followed each other. The big fat line is the total forcing, and the magenta line is carbon dioxide from oil, coal, and gas. How could this be? Well, it was because you see the line under the zero line is the cooling caused by air pollutants. So we have a massive paradox in the world, which is that roughly 1/2 degree Celsius has been camouflaged, hidden away from air pollution, which, by the way, prematurely kills 7 to 8 million people prematurely every year. So one massive environmental problem has been hiding a significant portion of another massive problem, what we are discussing today, namely climate change. From 2010 onwards, you see how this line starts going closer to zero, which is because we're cleaning up the cities in the world, because we have a 2020 policy of forbidding sulfates from bunker diesel in commercial shipping. We are simply solving the air pollution problem, which is one reason why we're bumping up the temperatures very rapidly, causing this black line to suddenly deviate off, injecting more heat than just carbon dioxide alone. The second explanation is that the planet is getting darker. Albedo, meaning that more solar radiation is absorbed on the planet. That's what you see in all these black spots here. Why is this happening? Well, it's major problems because of ice melt leading to darker surfaces, tree lines moving further northwards, but also cloud dynamics because we're changing the whole hydrological cycle. The color of the planet determines how much solar radiation that is absorbed on the surface, and it's getting warmer. And finally, the biggest concern, are we losing carbon uptake capacity in nature? What you see above the zero line here is fossil fuel burning over the past 150 years. Below the zero line in dark green is carbon uptake in the ocean. The light green is carbon uptake on land. Look at that graph. The more we stress the planet, the more the planet biogeochemically has been helping us, absorbing 50% of carbon dioxide in the ocean and intact nature on land. Now we're seeing the first signs of cracks in this system. Here you have a whole set of scientific papers showing how the temperate forest in Canada, the temperate forest in Scandinavia, the Brazilian part of the Amazon rainforest, and just look at this data from Finland, which just came out of the authorities in Finland recently, showing how the greenhouse gas emissions in Finland going down, the upper curve, but how the carbon sink in forests have collapsed. And today, over the past 3 years, Finnish forests are actually a net source, not even a net sink anymore. So this is what leads us to the conclusion that we may no longer rely on the stability and the buffering capacity of the planet, which would change directly the pace by which we need to decarbonize the global economy. Add to this tipping points. Tipping points are the big biogeophysical systems that have multiple stable states and control and regulate the stability of the climate system. We've mapped them. Here they are, the 16 big climate tipping element systems which are contributing to a stable climate. What I told you before here had no tipping point dynamics, but here you have them. 6 of them are up in the Arctic region. 1 of them is the overturning of heat in the Atlantic. The Amazon rainforest is there. 3 of them are down in Antarctica. The coral reef systems are there. They're spread across the entire planet. We have mapped them. For the first time, you see the list of 16 here. You see the burning embers diagram on scientific range of risk. The further to the magenta or to the purple line, the higher the risk is to cross a tipping point. This is the temperature range at which these are likely to tip. The small circles is the median average temperature assessment. Look at the top 5 here. Here we have those that are likely to tip already at 1.5 degrees Celsius. The Greenland ice sheet, the West Antarctic ice sheet, all the tropical coral reef systems, abrupt thawing of permafrost, and collapse of the Labrador Sea current. Dear friends, this is scientific evidence that 1.5 is not a goal, it's not a target, it's a physical limit. You don't want to exceed it because you're likely to cause irreversible changes that would even further amplify the rate of warming. But science actually tells us that we're wrong on one of these, and that's what you see here. The largest and richest ecosystem on land on planet Earth is the Amazon basin. This system stores over 100 gigatons of carbon, which is more than the remaining global carbon budget to have any chance of holding 1.5 degrees Celsius. Climate science shows that we may tip the Amazon rainforest at roughly 3 to 5 degrees Celsius of warming. So a very small risk. You know, we are heading towards 3 degrees Celsius, a disastrous future by the end of the century, but, you know, we are very unlikely passing beyond that. But when you bring in ecology and hydrology and forest science, the planetary boundaries, the whole picture changes. The assessment is that already at 1.5 to 2 degrees Celsius, we risk tipping the whole basin over to a degraded savanna state if we lose more than 25% of canopy cover because we change so distinctly the hydrology in the system. We are, to quote Professor Carlos Nobres, Brazilian leading climate and ecology scientist, very close to a tipping point in the Amazon rainforest. So we cannot separate nature from climate if we are going to have a chance of holding on to 1.5 degrees Celsius. Now, what I also want to share with you is that 1.5 degrees Celsius scientifically is, in the mainstream of the evidence we have, still an open window. But it's not open by never exceeding it. What you see here are the IPCC scenarios that can still hold 1.5, but after overshoot. We conclude that that is our only option today. What you see here will be breaching 1.5 somewhere between 2030 and 2035, so very soon, having a 0.1 to 0.3 degrees Celsius overshoot period until we may come back, at best, to 1.5 by the end of this century. It requires full phasing out of fossil fuels, but it also requires a second criteria, and that is the following. Why would the planet come back after us stopping the emissions from coal, oil, and gas? Well, the answer is simple. It is the resilience in the planet. It's the ocean system. It's biodiversity. It's fresh water. It's nitrogen and phosphorus. It is land. It is all the ecosystems that can continue to buffer and dampen both heat and carbon. We need, therefore, whether we like it or not, even if we focus only on the Paris Agreement, to take on the whole planet. And we have a framework for this, the Planetary Boundary Framework, which quantifies for all the 9 environmental processes that regulate the stability of the planet, what is needed to be done to be able to keep the health of the planet intact. 6 of the 9 boundaries, that's what you see here, are transgressed. So it's not so surprising that we're starting to see these signs of weakening because we're losing too much biodiversity, consuming too much fresh water, overloaded with too much nitrogen and phosphorus, and degrading too much of the land systems. So we're doing a double mistake. We are not reducing emissions, and we are unfortunately not keeping the resilience intact. And just to close, I promise, this is having impacts on the global economy. We're seeing 7% loss of income by 2035 if we continue on the path today, a report released at the World Economic Forum. We've recently done a study on what are the commitments already at 1.5 degrees Celsius for the global economy, which would potentially lead to a 19% loss of GDP by 2050. Not only that, that assessment has a very, very dramatic inequity dimension. Just look at how it hits so much harder on the global south with 30 to 35% loss in GDP from here to 2050, while you have the blue areas that nominally could even benefit economically on the short term. So we're talking big numbers, big impacts. The same with the food system. The food system has a market value of 10 trillion US dollars, but the real cost because of climate change, biodiversity loss, and health impacts largely very exceeds this number. But to transform the food system may cost us way, way, way less than those numbers. So we're talking here of win-win opportunities for food, for energy, and finally, the Global Commission on Economics of Water show the same thing. Climate change is changing the hydrology, impacting on freshwater availability, having double-digit impacts on GDP growth, particularly in low-income countries. So on all economic assessments today, both on energy, on biodiversity, on food, and on freshwater, they show the same conclusion. We're seeing double-digit impacts on GDP income loss if we continue on business as usual as today. So it's truly a juncture where we need to start, as has been emphasized so many times here this morning, to start implementation and delivery, not only promise new commitments. And that is actually 13.
Johann Rockström, thank you so much. And sorry for cutting you short.
It's stressful.
I stressed, no. Thank you so much.